Hey everybody, welcome back to this channel. Now that we've completed the course, I thought we could just take a step back and go over all of the base functionalities and kind of just walk you through how to do them. So let's go ahead and start here. Right, so this is the assignment for experiment 1, and basically we have our Arduino, and we have our 3 current limited LEDs connected to 3 different digital pins here, right? So this is what the circuit should look like, right? We have our LEDs, they have 2 terminals, and then they're connected to some resistors, and then the other end of the resistor is then connected back to ground. And let's just say that we have these on pin 2, 3, 4. So we go ahead and we make our sketch, and so this is the Arduino sketch. So we start off by defining our LED pins. Let's call it L1 on 2, L2 on 3, L3 on 4. Right, and then you obviously have to keep writing pound define. And then since I'm lazy, I'm also going to define this macro, PM, capital PM, and that's just going to be our pin mode function. And I'm going to define DW as our digital write function. So then we can start our setup. We want to tell the Arduino that we want to talk. We want to control all of these LEDs. So we're going to set the pin mode, sorry. So we set pin mode of L1 and we turn it, make it an output. And then we set the pin mode L2 as an output. And the pin mode of L3 as an output. And then in our loop, let's just say we want to do the AND gate. So we step through, we say for int I equals 0, I less than 3, I plus plus. And so let's just go through this 2-bit count, right? So we have 0, 0, 0, 1, 1, 0, 1, 1. And in unsigned binary, this count is 0, 1, 2, 3. So we count from 0 to 3. And then we're going to suppose that these are 2 bits. And then we pass it through an AND gate. So the AND gate is true when both of the outputs are, or when both of the inputs are true, right? So it's only going to be true here. And then we encode the LEDs. So if I is 0, we go ahead and write L1 low. And then I'm just going to write dot, dot, dot. So these are all going to be low. Right, and you can just kind of like follow this logic. Right, and then if we say else if I is 1, then the only thing that we're going to be turning on is B, right? So digital write L2 is high. and then we turn the other ones off. And you can just go ahead and follow this logic. So 0 is mapped to low, and 1 is mapped to high. And so A is mapped to pin 1, sorry, LED 1, B is mapped to LED 2, and A and B is then mapped to LED 3. And following that logic, you should be able to make that just 2-bit up count and for this AND gate. And you also want to delay at the beginning or the end, wherever you want to wait a second so you can actually see what's going on here. And that pretty much wraps up this first base functionality. So we can take a look at the second one. So for the second one, everyone was kind of having trouble here, but basically we have our Arduino, and we're going to have a potentiometer. We're going to be applying 5 volts across the potentiometer. And so we've got our potentiometer, and it's got these 2 pins. And basically we take our Arduino, connect one end to 5 volts, connect the other end to ground, and then we have our 5 volts across that potentiometer. And then we want to come in at the center tap, and I think usually it's on this other side here. So there's that center tap, and we come in with a digital pin. So let's just say we use pin 2 again. Why not? So we come in with a digital pin, and we also come in with an analog pin, just so that we can look at the voltage here while we turn the potentiometer, right? So on the potentiometer, I guess that's not a good representation of it. So the potentiometer is basically a resistor divider network, and it's variable, so we can probe the center tap here, and we can see the change in resistance, right? So inside of the potentiometer is this long resistive strip, and we have this knob, or it's kind of like a dial, right? And you can dial in the different resistors. So at one end, across this, so we have our 2 voltage potentials coming out like this. And at one end, if this is 5 volts and this is ground, at one end, we read 0 volts, right? There's no drop across 5 volts and this center here. But then if we turn it, it's maybe like halfway, then we see a drop of about 2.5 volts. And I think this particular one that we have in our kit is a total of 10 kilo ohm potentiometer, right? So when we have this reach this halfway point, then the resistance on either end is going to be 5K. And that's just interesting, kind of trivial knowledge probably at this point. But so we have our center tap, and it's connected to our digital pin and analog pin, and we're going to be reading it. And then we are going to start at analog 0, and then in steps of about 100. Right, so analog 0 refers to the voltage, and so when we're all the way at the 5 volts, our center tap is connected, it's tied up to 5 volts. So to start at analog 0 would be to crank the potentiometer all the way to this ground terminal, right? So in this case, if we have a 180-degree rotation, then we turn it all the way clockwise. And then to turn it counterclockwise would be to crank it up to 5 volts. So we start at analog 0, and we measure the voltage at the center tap and ground, and then we plot the voltage as a function of the analog reading, right? So we also need to have some kind of multimeter. Actually, not even a multimeter. We're only measuring voltage, so you just say voltmeter. And then we're going to be measuring the voltage here with respect to ground. And I think that pretty much sums up the explanation for the space functionality. I think in future editions, we're just going to take out part 2 here. I think this experiment is kind of challenging conceptually, probably for those of you first seeing it. So we connect a voltmeter there, and our goal here is to make a calibrated voltmeter using the Arduino, right? So our Arduino is going to use this function to determine what voltage it is reading, because right now the analog reading, right? So when we have our analog reading, what's happening is it's returning a value from 0 to 1023, and we could directly convert that into a voltage, but it's not going to be a perfect reading, right? So we have this calibration factor B that we can determine experimentally, right? So we plot the voltage as a function of that analog reading to determine the calibration factor there. It's just additive there. So anyways, we can go ahead and come in with our Arduino sketch now. So we have our setup, and we want to set the pin mode of our digital pin. So that's going to be 2. So I'm going to define some, let's just assume that we've already defined pin mode and digital write. So what we need now is a digital pot pin and an analog pot pin. Right, and then pot D is going to be tied to pin 2, and pot A is going to be tied to pin A0. So we set the pin mode. You don't have to set the pin mode for analog pins because I think they're bidirectional in nature. But so we set the digital pin, so we set pot D, and we're going to be reading in a value. So this is going to be an input, right? Because we're looking at the voltage there, kind of. And we also need to start the serial monitor. So if you look at the documentation on serial, you have to start, all right, so to open with the serial.begin, and you just specify the rate at which we're talking at so that the Arduino and the computer can understand each other. And so the serial monitor is this connection between the computer and the Arduino. They're talking to each other. So we have our serial begin, we have our pin mode set up here. And now what we need is the loop, so void loop. And what we're going to want to do here, so first we're going to read each of the values, and these are going to both return some integer value. So we can say int, we'll call it, let's say, well, up here we call it A for our analog reading. So we'll call it D and A for digital and analog. So D, we're going to say that's going to be our digital read, right? So up here we can define a digital read. DR is going to be digital read, and let's just assume that I've already, I guess we're not really going to be writing anything, so that's not important. So we do a digital read of our digital potentiometer pin. Oh, I guess that's the only thing you have to specify, right? So we read that, we store it in there, and then A, we do an analog read. There's our macro. So we do an analog read on our analog pin. And then we want to display it. So we print, let's just say we're analog. And then we serial dot print with a new line. So this appends a new line character. So then we print out our analog reading. And then we want to do the same thing here for digital. Oh, geez. We do the same thing here for digital. And I'm clearly too lazy to write that out. So serial.print digital. And then we print out with a new line, it's D value here. And then what you were supposed to do during the lab session was gather data to determine some other things. So we want to determine what the slope is, right? So we have some float M, which is whatever you found it to be. Let's just say it's 1. And then we had some float B, which is that y-intercept. And we'll just call that 1. Right? I don't know what those actually are, because it depends on the measurements that you made during lab. So we have our float. So then what we want to print then is the calibrated voltage. Reading, and then we print out this voltage reading, which is M times A. Right, so this is going to be an asterisk plus B. And you might have to convert A to a float. So let's just start off by defining them as floats anyway. So we print out M times A plus B. And that's actually all that you needed to do, right? Other than this part 2, which I've decided to take out, and in future editions, I'll probably refactor that into some other assignment because this one's pretty beefy. So there's that. And then here's base functionality 3. So we have our Arduino. And we have our 7-segment display. I'm just going to call that segment display. And so each of these segments have a letter reference A, B, C, D, E, F, G, and this decimal point. And those all correspond to, I think there are 10 total pins here, maybe, because there's 7 of these, decimal point, and I think there's multiple grounds. So it's actually 8 plus the 2 grounds, yeah. So these 2 are both tied to ground, I believe. Right, and you can find all this over in the Canvas page on the user manual. Has all the information. If you just open up the user manual and navigate to the wherever the last time I put the user manual. There we go. We open up the user manual. We go down to table of contents and we find the segment display. So here's lesson 27 that has, looks like it uses it. Right here's that drawing that I just made. So there's the two ground pins in the center of our device here, and you can see the little arrows indicating which pin corresponds to which segment and what you want to do then. Right, so for example, we have this controls pin A here, and then we can maybe tie that. So these are all going to be tied to a digital pin. And then I think something else that was important was to connect the ground pins through a resistor so that we don't damage each anode, each of these LEDs that are inside effectively. So we have our pin A here. I'm just going to start with an example of A. And I'm not going to walk through how to code every single one of these examples. I will go through the logic of printing out the sequence. But so we have pin A. Let's just say that we tie this to pin 2, 3. So we have 7 of these because we're not going to use the decimal point. We're just going to turn that off. So 2, 3, all the way up to 10. No, 9. The pin A we're going to tie to 2 here. Pin B is on 6. And then I'm not going to, I'm going to tie that to 3. So this is B. That controls B. And I'm not going to walk through how to do all this. I will go through some examples of the table. So we're doing hexadecimal values, so 0, 1, 2. So this is our hex value. This is our segment pins. So for hex 0, we need A, B, C, D, E, F, right? So that'll draw out something that looks like this, which is our 0. And then for 1, we want BC. Right, so there's 1, or FE, however you want to do that. And then 2 is AB, ABG, ED, right, to draw this 2. And then you can work out the rest. I'm not going to tell you how to write characters here. So this is going to be A, B, C, D, E, F. This is going to be B, C. This is going to be A, B, G, E, D, A, B, G, E, D. Right. So this is really more of a tedious experiment, just cranking through the logic of how to control this 7-segment display. It's the first part. And the second part is a little bit more challenging. So we're going to have a sequence, right? So let's just say we have our setup. So in setup, I'm not going to tell you how to do this, but we set all segment pins to output, and we're controlling them with the Arduino. So we do that, and it looks like we also need a buzzer. But buzzer tone should be more of a trivial task, so I'm not going to go over that. I'm sure you can find the reference on how to use the buzzer, but pretty much you're just applying some kind of pulse width modulated tone or pulse width modulated signal to it to play a tone. And I don't even specify what kind of tone, so you could probably just write high and turn on the buzzer, and I'm sure that'll be sufficient there. So the loop then is what is more challenging here. And so also in setup, we probably want some global variable flags, right, to tell us how to go about starting this loop, or maybe not, let's see. So let's just crank through the logic here. So probably want to start with a flow chart just to see what it is we're doing, because we're no longer dealing with these trivial tasks. So we start, our program starts. We will probably want to set the mode. And so we have some kind of mode that indicates if we're writing in binary, or if we're writing in decimal, or if we're writing in hexadecimal. So let's just say we start off in binary. It doesn't matter where you start off. I just think this is probably the easiest. So we set the mode to binary. We want to set, we also want to have some kind of count, right? So we're going to be counting from 0 to 1 over and over when we're in this binary mode. So we set the count to 0. So we set the count to 0, and then we want to display the count on the segment display. So we display the count. And then we want to increment the count. Right, so we just say count is equal to count plus 1. So we increment the count, and then we check is count at the max. Count. And the max is going to depend on the mode. So I guess in our case here, once we have the mode, we need to set the max. Set the max to 1. We increment the count, we check if it's at the max. If it is at the max, then we play the buzzer tone. So we play the buzzer tone. So this is going to be yes. If we are at the max, we play the buzzer tone. If we're not at the max, we set the count back to 0. It's going to be, oh, actually, sorry about that. We play the buzzer tone and then we set the count back to 0. If we aren't at the max, then we go back to displaying the count. Right, so then we enter this loop of displaying the count, incrementing it, and we keep doing that until we're at the max. So somewhere in here, we also need to check if there's a button press, just so that we can change the mode. Maybe we do that here. So we move this increment functionality down, and then we loop it back up to there. And then here we check if there's a button press. So if we've registered a button press here, and then if we haven't, we just continue on with their regular functionality. But if we have registered a button press, and then we need to change the mode to decimal. All right, so let's just move this because this is going to be more involved than I thought here. So then we set mode to decimal. If there is a button press here. So we set the mode to decimal, right, and that entails setting the max to 10, or I guess in this case 9. We're dealing with single character. So we set the max to 9. So that's when there's a button press. We set the max to 9. And then we go back to setting the count. Or we go back to checking the count here. Go back to checking the count. Or let me see the spec here. Oh, so when we register a button press and when we reach the end of the sequence, so sorry about that. Let's erase this. So instead of setting a mode here, we need to set a flag. We need to tell the system that we registered a button press and we need to change the mode to decimal. But we can only do that once we reach this count max here. So we go back here to incrementing the count. And then we go back, right? So then we enter back into this loop where we check if it counts at the max. And if the max is if the count is at the max, then yeah, we still play this buzzer tone, but we're also going to check if the flag was set. And then if it's not, then we can continue. But if it is, then we need to update the count or update the max. So set new max. And then we loop back to setting the count to 0, and we enter back into our loop here. So I'm going to be more general here and just going to down here set number system flag. Right, so inside of here, inside of this set number flag, if we're in binary, then we need to set to decimal, and if we're in decimal, then we need to set to hexadecimal. And so that's kind of the logic worked out. I think that this should be sufficient for getting started. Doing it, I'm not going to walk through how to do all of this in Arduino because this is pretty straightforward stuff. I gave you example code on how to drive the segment display, but you should know how to set variables, how to kind of like encode different modes that you can check, right? So we have our binary mode and we have our decimal mode, and you should be able to have decision blocks like this. So right, this is going to be like an if statement, another if statement. I showed you how to connect it effectively. I showed you how to crank through the flow chart. And if you still need help after that, feel free to let me know. But that's for base functionality 3. Base functionality 4. So we have our Arduino again, and we have some IR sensor. And I don't remember what the pinout looks like actually, so let's just pull it up here. So the IR receiver module has 3 pins, and if we look at the schematic, so we have ground at the top, we have power, so our 5 volts in the middle, and we have data at the bottom, and data is connected to a pulse width modulation pin. So ground, I'm just going to connect this backwards here. So we have our module ground, and I think data's in the other end of ground. Let's see, it's VCC, this is data. And so 5 volts. And let's use pin 11 like they used. So then we have an LED network, right, that we're going to be controlling again with some digital pin here. So let's just say we have pin 2. And that will be our status LED. And then we have another network of 4 LEDs. These are all tied to ground here. And let's just say we have pin 3, 4, 5, 6 that are then connected to these guys over here. And I realized when I was trying to explain this during office hours how involved this process is. But basically, the remote. So we have a remote, and at the top of the remote is a little light bulb, right? It flashes infrared light, and the receiver has another kind of like bulb looking thing that takes in the light. It sees the light, and we can use some example libraries. And so we use this IR remote library, I think, .h. We include this library, and we're able to then decode the data. And if you look into the library, and I think we can pull it up on Canvas here. So I provided the kit example code. This is just someone's implementation that Braden found online here. So we can pull up this lesson 14 IR receiver module, and we can take a look at the code in here. We open up the Arduino script. So he includes this IR remote.h, and we walk through how to install that and whatnot previously. But it's got a lot of layers of functionality that we can't see. But what we can see is that we have some hexadecimal value stored in this results.value while we're translating the infrared code. And this is where our data packet is. And you'll notice that we have 8 hexadecimal characters here, which is where I talk about nibbles. So we're looking at the different nibbles. So a nibble, right, so we have 4 hexadecimal values in our results.value here. So inside of results.value, while we're looking at this example script, we have this 32-bit data packet. right? And these are just a bunch of different hexadecimal values. So let's just look at the first one here. So FFA25D. So let's just say, for example, we have our FFA25, 1, 2, 3, 4, 5, 6, 7, 8, 3, 4, 5, 6. Okay, so when it's only 6 bits, FFA25D, then we actually don't need these upper bits, right? So it's kind of like, let's say I have the number 300. Well, that's the same as 0300, 00300, right? You can put these zeros in front of it and it won't change the value. So it's the same idea with hexadecimal number system and pretty much any number system, right? So if we had binary, let's say 0. If we have 1, well, it's the same as 01, same as 001. It doesn't change the meaning here if we append these zeros to the front. But anyways, so we have this 32-bit data packet, and what we want to do is take a look at each of these nibbles, right? So 8 bits is a byte, and this is 8 bits, so that's kind of difficult. So instead, we just take a look at one hexadecimal character, right? So this is one nibble. So this is a nibble. Call that. We'll just say that this is nib1, and this is nib2 over here, and so on. So then to get this first nibble, what we want to do is zero out everything else. All right, so we say nib1, and this is just going to be some integer value. So we have int nib1, nib2, and so on. And what we want to do is we take our results.value, and we want to take all of these bits and set them to 0. And we call it a clearing operation. So we clear it by ANDing it with this hex f. And it's hex f because we want to get these 4 bits here. All right, and that's going to be our nib1. Our nib2 is going to be this results.value. And we want to get this second place. Right? So we want to get this. So we AND it with the hex f0. Right? So we clear out nib1, we clear out everything that is after nib2, but then it's in the incorrect spot, so we need to shift it over by 4 bits. So this is it's a bit shifting operator here. It's called a right shift. We're moving it over to the right. And so we shift it over, we take, so say we have one here in position 5, right? So we shift it over to position 1 here. And we do that for all of the bits in nib2. We shift them all over to get them into nib1 position to make sure that we have the right value here. So that's how we extract the data packet one bit at a time here. And we want to start decoding from the most significant nibble. So that's actually going to be up here. And that's just because this is right, this is the biggest value over on the left here. And it depends on how you interpret the data too. So most significant and least significant nibble are kind of arbitrary in this case, unless we know the order of the data that's coming in. So I think in future editions, I'm going to not mention that. Just understand that we have some data packet here, and we're trying to decode it one nibble at a time. And then, so the logic then to write out these to an LED is pretty simple. So we have our nib1, we say for int I equals 0, and we have 4 bits, so we go up to 3, I plus plus, and then we have our pins on 3, 4, 5, and 6. So we do a digital write to pin 3, and we're going to take nib1, and we're going to clear everything except the first position here. So we AND it with 1. And that's to get the first nibble, the first bit in the first nibble. So then on pin 4, we then AND it with 2. And then we shift all of that over. We AND it with 2, and then we shift this over by 1 bit to get our second bit in nib1, and so on, right? So just taking a look at, I'm not going to do all of this, but I will explain it, hopefully, so that you have a better understanding. So let's just take a look at this first nibble here. So we have D, the hex D, EFD. So then that's going to be 1, 1, 0, 1. Sorry. So A is 10, B is 11, C is 12, D is 13. We have 8 plus 4 plus 1. Yeah. Okay. So this is our hex D, and this is going to be our first nibble. So then our LED network, right, should have all of the LEDs on except for the third one here. Right, so if we look back up here, when we have our hex D, it's going to be on, off, on. And we do that by iterating over the nibble, and we set, right? So bit 1, this nibble has 4 bits, bit 1, bit 2, bit 3, and bit 4. So bit 1, we want to clear out all of these, right? So we AND it with the hex, with the 1. And for bit 2, we want to clear out these 2 and this 1. So we AND it with the hex, with the 2. And so 2 is 1, 0, 1 is 0, 1, 3 is, let's just walk in order here. So what we want to do is AND it with something like this, so that we can obtain each bit let's just say we have nib1. So nib1 is this 1101. And we have our 4 bits. And bit 1 is going to be nib1 and this 1. Bit 2 is going to be nib1 and 2, right? So this is 2 in binary. And then bit 3 here is a 4 in binary. And bit 4 is an 8 in binary. Right? So we just erase all this. So we AND it with 1, AND it with 2, AND it with 4, AND it with 8. And then we have to do that shifting operator again to get it in the correct place to determine whether or not we want to turn on the pin. Right, so we shift this over by 1 bit. We shift this over by 2 bits. And then we shift this over by 3 bits. So here we have the bits all moved over into the ones place. And then to turn on the LEDs now, we have to do digital write. So like if bit 1 then we do a digital write to our pin 3 here, I guess. And then we have to check each of them, right? So then if bit 2 is high, then we do write to pin 4 and so on. And then you probably also want to turn them off each time. And then so we take each nibble, we write all the bits to the LEDs, we wait a second, and then we work on the next nibble. And that should be hopefully a straightforward process by now. But if not, of course, feel free to let me know. So there's base functionality for part 4. And then part 5 here, I think everyone was pretty much able to get this part for the base functionality, but basically if we go back to the Arduino kit, I can talk about it briefly here. So the kit manual here. So we're working with motors. Let's see. So we have our DC motor experiment. And we have our Arduino. We have this L293D chip, which is then used to control the motor. And the motor has these 2 terminals here. So coming out of this 293D chip is these 2 motor control pins. I think it's, if we go down to the diagram here. So we have out 1 and out 2, which are controlling the motor. Out 1, out 2 coming out of those chips, right? So the Arduino can't really control these 2 pins. It's just what is this chip is using to control a motor. So the motor takes in an enable pin. 2, like these input pins are kind of like direct, they control the direction, and then ground pins and the motor driver. So we have this power supply module here, and this is kind of just connected directly to your breadboard. And then it's got some 5-volt ground that we tie back to the Arduino, and then we tie this to the power motor here, so V motor. And then we have our enable pin, and I think this is actually a pulse width modulation because we can step up, and so we have 255, 128, and 0 for full speed, half speed, and then this is just off on that enable pin. And then we have our 2 direction pins. I think it's called N1 and N2, it looks like. So these are digital pins, so we can just use like 2 and 3. And then this is some pulse width modulation pin. We can use whatever pin there. So we have our 2 direction pins. And this is kind of like, I don't know if they had a good. But we have our 2 direction pins, and to set it in one direction, we change this to high, we change this to low, and this counterclockwise and clockwise directions are kind of arbitrary. But to change it into this other direction, we change the polarity of these 2 pins basically. And that will do that. And then it looks like we have an LED. So we have 2 indicator LEDs, right? Just tied to a resistor network here. And then connect it back down to ground. And these will determine the speed mode and the direction. Oh, two LEDs for the direction, one LED for the speed mode. And then I guess we have the, in addition to the motor, we also have the ultrasonic distance sensor up here. And I believe that has four terminals, but we can take a look. So we pull up the user manual again, go to lesson 10 here, and it's got VCC, trigger, echo, and ground. So ultrasonic distance sensor, and it's got VCC, trigger, echo, and ground. So ground can just be tied back to the Arduino ground. VCC, I think, can just be tied up here to the 5 volts. Trigger and echo, one of them is I think trigger is an input going into the ultrasonic distance sensor, and then echo is coming out, going into the Arduino. But I guess, so this isn't super helpful, but these are both going to be digital pulse width modulation pins. So we connect this over here. 2 separate pins for trigger and echo, and these are both going to be pulse width modulation, it looks like. So there's a schematic pretty much. And the logic is pretty trivial. I kind of just followed the example for one of them. I believe it was for the ultrasonic distance sensor. So we can go up to the kit code, kit example code here, and then we can pull up the, let's just take a look at, let's look at the DC motor first. Let's see what was there. So the DC motor control is pretty trivial, right? You just turn on whichever direction that you want, right? So you set N1 high, N2 low, or N1 low and N2 high, and then you set the speed with that enable pin, you can drive it that way. So I'm not going to go over how to do that, but that's what that example is doing, it looks like. So let's just take a look at the ultrasonic distance sensor here. Okay, somehow ended up there. So it looks like here we set the pin mode for the trigger pin as an output. Yeah, so the trigger, we're triggering the sensor with the Arduino. We tell the sensor, hey, start sensing the distance, and then on the echo is going into the Arduino, right? So we can kind of just draw the direction of the signal. So the trigger is coming out of the Arduino and going, the echo is going into the Arduino back there. And then here's just some example code on how to use it. So it looks like it stores the distance, right? And you can just copy this loop here. But it looks like it's storing the distance over in this answer. And so there's that answer, the distance in centimeters, and you can also print it in inches over there. But you probably want to just delete the part where it converts answer into inches, because we're just looking at centimeters for the experiment here. And so we have centimeter, 100 centimeter, we run it at full speed. Between 5 and 100, we go half speed. Less than 5 centimeters, we reverse the direction. And this is all pretty straightforward, hopefully logically. So you should be able to make up a flow chart on how to do this. And if you have more questions on that, right, we can talk. But that's for the space functionality 5. And then lastly, this isn't really a base functionality, but I thought to the habitat control system as a fun little project. So I'll just talk about it briefly here. We have, again, the Arduino. These are all kind of Arduino projects. And we have a, we want to have these resistor networks for our photoresistor and for our thermistor. T, so photoresistor and thermistor there, and these are both actually going to be tied up to 5 volts here. And you can use whatever, maybe 1K or so. I think some of the example scripts have something else. But over here, we're going to be recording 2 different analog values. So let's just say we have A1 to the thermistor, A0 to the photoresistor. And if we just take a look at one example, right, so the photoresistor, as a function of light intensity, the resistance, I believe goes, well, we can just pull it up actually. It doesn't really matter. I think the resistance goes down. And then for the thermistor, we have resistance as a function of temperature. And I believe that the resistance goes up. So basically, in the example code, there are ways of using the thermistor here in this thermometer exercise or lesson, right? And it's got this resistor network that I just drew out. So we have 5 volts, we have an analog pin, and we have some arbitrary other resistor in our thermistor. And here we're just able to look at the temperature. We can determine the temperature based on these thermistor values. But you want to make sure that you're using the same R2. Right, so in this case, he's using a 220 ohm, it looks like, resistor. That's tied to the thermistor here. So his voltage, his thermometer readings are calibrated to this 220 ohm resistor at the top of our network here, tied to the 5 volts. So if you want to use that example code, use 220 ohm resistor. And then if we go down here, let's see, for the photocell, there is maybe not an example. Anyways, the photocell works the same way, but I guess we'll have to derive how to go about calculating the resistance there. So let's just say we use 220 ohm for the photocell and for the thermistor here. So we have 220 ohms here, 220 ohms here. And what we're then looking at is something like this. And so we have 5 volts here, 220 ohms here. And we have some resistance as a function of intensity, so RP or something, the photoresistance. So RP, right, the voltage across RP is going to be, we take our 5 volts and we take 220, so then we take RP divided by the sum of these two. And so it's just a simple voltage divider network here. And that's going to be the voltage there. And then I said here that I characterize that RP at 30 kiloohms is when we have our switching logic. So then we say our switching voltage here is going to be then 5 times 30K divided by 220 plus 30K. And just do that right here. So then that's going to be at about 4.96 volts is when we want to switch. And then since we have an analog pin connected there, right, so that's going to be right here, we have our analog pin. So our analog reading should then be however we convert that, right? So we take our 5 volts, I think, and remember, so then it's being mapped from 0 to 1023 for this analog reading. So we take 1023 and we map this ratio of 4.96 by 5, I think. And that gives us 1023 times 4.96 divided by 5. That gives us an analog reading of about 1014 there. So once we measure an analog reading of about 1014 is when we want to turn on the LED. Now you have the example code for getting the temperature, and then there's also example code for using the LCD display over here, LCD display. So yeah, this is a little bit more involved, but we can walk through the LCD display here. So it's a 16 by 2, that means there's kind of like 16 columns for us to write in 2 rows, I believe. And then you need to pay attention, right, to these different pin mappings that the library uses. So if you're going to use this example code, you need to match these pins. So we have RS on 12, enable on 11, D4 on 5. So then if we go to, so on your LCD module, or on the LCD device itself, it has these pins labeled. And you need to make sure to connect the Arduino pins, right? So these numbers 12, 11, 5, 4, 3, and 2, these correspond to pins on your Arduino. So in this example, it's just printing out hello world. I believe there's also an example of the temperature. So you can find that and play around with it. Right, here's the thermometer, and I think this thermometer lesson is also printing out, to the LCD. So follow this to print out temperature to the LCD and try to get it so that you're only displaying the temperature in Celsius, because then you'll also want to display the photocell resistance here. So with that, I think that's all I wanted to talk about for all these base functionalities. I think these were some of the most challenging concepts that I want to make sure that everybody kind of understands at least. But thanks for tuning in. Thanks for being an awesome class. Hope to see you guys in the future.